GS Reuse, Temporally Adaptive Screen Space Reuse for Accelerating 3D Gaussian Splatting. Our research focuses on addressing the performance bottlenecks in real-time, high-fidelity neural rendering, particularly for demanding scenarios like virtual reality applications and long video sequences. Neural rendering has recently made significant strides, and 3D Gaussian splatting has emerged as a powerful explicit representation that achieves a great balance between quality and efficiency. However, achieving real-time performance remains a major challenge in large-scale urban scenes and VR systems. VR rendering, in particular, imposes strict latency requirements, typically demanding refresh rates above 90 FPS, along with stereoscopic rendering for both eyes, which effectively doubles the workload. To accelerate 3D GS, existing methods aggressively reduce the number of Gaussians, but this often trades off high-frequency details for performance and necessitates scene ray training. Furthermore, in continuous video sequences or VR navigation, adjacent frames share significant visual overlap. However, current 3D GS pipelines render each frame independently, leading to massive redundant computations. Existing video interpolation or extrapolation methods rely heavily on neural networks operating in the image domain. They cannot be directly applied to point-based 3D GS rendering, and their high latency makes them unsuitable for real-time applications. To identify optimization opportunities, we analyzed the 3D GS forward rendering pipeline. The process consists of 4 sequential stages: splatting, tilling, sorting, and compositing. According to our experiments, the splatting and tilling stages account for only about 2% and 8% of the total rendering time, respectively. The real bottlenecks are the sorting and compositing stages. If we can adaptively reuse previously rendered contents to minimize the workload of these two most expensive stages, we can significantly boost the overall frame rate. Driven by this analysis, we propose GS Reuse, a lightweight screen space accelerator that acts as a drop-in solution. Unlike object space optimizations that modify Gaussian representations and scale with scene complexity, GS Reuse operates entirely independently of the number of Gaussians. As shown in our pipeline, we introduce an additional reusing stage prior to the standard rendering pipeline at time t1. The reusing stage warps the historical content to the new view, generating two things: a set of reusable tiles TU and a critical tile level mask M. This mask is passed directly into the standard 3D GS splatting and tilling stages. During the tilling stage, any tile marked as valid by our mask is completely skipped during the key value pair generation. As a result, only the tiny fraction of remaining, non-reusable tiles TR actually proceeds to the computationally heavy sorting and compositing stages. Furthermore, once frame T1 is generated, its result can be continuously passed forward to serve as the source for generating frame T2, and so on. The core of our warping strategy is the Gaussian Splatting Motion Vector GSMV. Using the depth map and camera poses from the teeth frame, we back-project pixels into world coordinates and then reproject them into the camera space of the T+1th frame. The displacement between these screen locations gives us the GSMV. When the view changes, multiple pixels may map to the same position, causing background content to mistakenly overwrite the foreground. To resolve these occlusion conflicts, we implemented an occlusion-aware composition strategy. By using a depth buffer and CUDA atomic operations, we guarantee that pixels closer to the camera are prioritized. However, direct frame warping introduces scattered invalid pixels or holes due to disocclusion. Since 3D GS renders in 16:16 tiles, even a single invalid pixel forces the entire tile to be ray-rendered, drastically reducing reuse efficiency. To maximize the number of reusable tiles, we designed a pixel filtering module. We first apply a morphological closing operation using to identify isolated invalid pixels surrounded by valid regions. We then apply a depth-guided bilateral filter to fill in their colors. This foreground-aware filtering prevents color bleeding across object boundaries and significantly increases the proportion of tiles that can be safely skipped. This is the overall pipeline of our tile-based temporal reuse strategy. First is the frame warping stage. We take the rendered image and depth map from the previous frame T and compute the Gaussian splatting motion vectors for the new view. Combined with our occlusion-aware composition, we warp the historical content to generate a raw warped frame alongside an initial pixel-level mask. Next, move to the pixel filtering stage. By applying the morphological operations and depth-guided bilateral filtering we just discussed, we safely inpaint these sparse invalid pixels. This crucial step allows us to upgrade the pixel-level mask into a much cleaner tile-level mask, maximizing the number of fully reusable tiles. Finally, in the tile-based reusing stage, the tile-level mask is fed directly into the 3DGS renderer. The renderer uses this mask to completely skip the valid reused tiles and only performs the expensive sorting and compositing operations on the few remaining invalid tiles. We then simply combine the newly rendered tiles with our reused tiles to output the final, high-quality frame T+1. Our method also supports incremental rendering, meaning frame T+1 can directly serve as the source to generate frame T+2, and so on. While multi-frame reuse further enhances rendering speed, repeated projection can accumulate errors. To maintain high visual quality over long sequences, we actively discard the most error-prone pixels, specifically those we inpainted during the previous frame's generation, before producing the next frame. Our experimental evaluations showcase the strong advantages of GS reuse. We compared GS reuse with state-of-the-art video frame interpolation methods, like IFNet and Rife, and extrapolation methods like DMFEN. Neural network-based methods often struggle with complex scenes. They tend to produce overly blurred results and fails to capture thin geometric structures, like the missing bicycle fork in this example. In contrast, GS reuse relies on precise geometric transformations. It reliably preserves structural integrity and sharp details without introducing ghosting or distortion. This table compares the average frame generation time at high resolutions. Existing video generation methods' latency is far too high for strict real-time systems like VR, ranging from nearly 10 milliseconds to over 27 milliseconds per frame. Because GS reuse is entirely non-learning based and operates directly on the rendered outputs, it requires only 2.64 milliseconds of processing time per frame on average. This low latency is what makes our method well suited for demanding real-time applications. It is important to emphasize that GS reuse is an orthogonal, plug-and-play solution, which means it can seamlessly integrates into existing acceleration frameworks. We integrated GS reuse into several representative pipelines, including standard 3DGS to DGS, light Gaussian, taming 3DGs, and mini-splatting. As shown in these runtime charts, regardless of the underlying pipeline, GS reuse consistently delivers a highly stable and significant additional speedup, ranging from 1.5 times to 3 times depending on the baseline. Finally, we evaluated how GS reuse performs in large-scale scenes. To demonstrate this, we integrated our method with City Gaussian V2 and tested it on large-scale datasets like Go and Matrixity. Our method achieves an average speedup of 1.6 times across these highly complex scenes. For example, look at the MC aerial scene. By enabling GS reuse, we push the rendering speed from 63 FPS to a remarkable 100 FPS. Crucially, this efficiency does not come at the expense of visual fidelity. If you look at the dark error maps on the right side, the structural and color differences between our reused frames and the fully rendered baselines are extremely minimal. The average root mean square error is only about 0.02. In conclusion, GS reuse introduces an innovative temporal reuse perspective to 3DGS. As a plug-and-play, scene-agnostic solution, it significantly minimizes redundant computations and opens new possibilities for real-time neural rendering at larger scales and on resource-constrained VR hardware. Thank you all for listening.